Du coup, bienvenue à tous. Welcome to everyone. Sorry, we're gonna switch to English. So to this second Edu IHM webinar. So the webinar of the working group for HI for Education from the GDR IHM. And today we're gonna listen to Vincent Casamayou, who is a research engineer at the University of Bordeaux. Before being a research engineer, Vincent was a PhD student in the BIVWAC team at Inria Bordeaux and with the University of Bordeaux. Also working on quantum physics and education. And so today he will talk about his work about making quantum physics manipulable, designing tangible and digital tools for education. So Vincent, now you can go. The floor is yours.
Okay, thanks, Arno. So hello everyone. So I'm Vincent Casamayou. I'm an engineer researcher now at Bordeaux University, and I will present my work that I did about designing tools to help students and teachers during their optics and quantum physics courses. So all this work was done during my year at Inria Bordeaux, starting as an engineer, then as a PhD student, and now I'm being an engineer once again. But now I'm also working with the LITEC physics team in Bordeaux University. But first, let's talk a bit about physics. So imagine that you are Isaac Newton facing an apple falling from a tree. So this apple behavior is ruled by classical physics. It has well-defined characteristics. If I throw the apple, I know its trajectory, its speed, and I can calculate where it will fall. But now, imagine that you are facing an atom or a subatomic particle, which is something really more complex to think about. Well, the rules that apply to this particle no longer depend on classical physics, but on quantum physics. First, you generate a problem of perception. For particle physics, we go from a macroscopic to microscopic or below scale. And for example, at this scale, a pair of properties such as speed or the position cannot be clearly defined at the same time. If you know precisely one, you cannot know precisely the other. So over time, physicists have developed several mathematical frameworks to describe this concept. And the main difference here is that we don't really talk about specific values, but more in terms of wave function. For example, the wave function that will describe the probability of finding the particle at a given position. Finally, it's important to note that in quantum physics, the observation of a phenomenon completely alters the observed system. And that's make it really difficult to actually visualize quantum physics phenomena in real life conditions. So all these concepts that I briefly introduced have led to the first quantum revolution and the development of a new branch of physics that is called quantum physics. And so physicists have studied how this physics works, and in turn, it led to new technologies that now are the heart of our modern electronic systems. But since the beginning of the 21st centuries, Dunning and Milburn have described what they called the second quantum revolution. Here we seek to apply concepts from quantum physics to develop application, for example, in fields such as computer science or sensor technologies. However, to progress with this quantum technology, we will need to train not only researchers, but also engineers and technicians. And so, the teaching of quantum physics must adapt to prepare students who are pursuing career in these quantum technologies. And we will see that this claim is often linked to the fact that previously quantum physics education had to deal mainly with one type of student, and now they wanted to go in research, and now we are moving to multiple student profile that will go into all this kind of career. So to begin with, we will identify together the challenges that hinder the learning of quantum physics. Then I will focus on the project that I worked on, which is focused on the practice of optics. And so I've been working on an approach from classicals to quantum physics, since we'll see that the problem that I have encountered not only limits to teaching quantum physics, but applies to physics in general. Okay, so let's start with the context. So to understand the challenges of teaching quantum physics, we will examine how the teaching practice evolved. So first, quantum physics education has for a long time been dominated by the shut up and calculate culture, named after a famous quote from David Bermin, a physicist. It means that the mathematical formalism was taught while downplaying all the concepts and the importance of the concept. And this practice still persists to this day and was documented by Johnson and al. In 2018. But at the beginning of the 21st century, conceptual learning gained popularity, largely thanks to the work of Chandralekha Singh, who researched student understanding of quantum physics. And she realized that there was a significant disconnection between student ability to apply the formalism and their actual understanding of the phenomena. But at the same time, in the following years, the conceptual learning was also reinforced by the use of digital tools, which helped to visualize abstract and counterintuitive concepts. So if we talk more about student difficulty in themselves, in 2021, Boucher and his colleague launched a new study to build on Singh's work and to categorize the difficulty faced by the students. Among them findings, I will highlight two of them, two categories, the concept and the language. And they also offer a solution for each of these categories, experimentation on one side and the use of digital tools on the other. And also I will focus on these two approaches and the relation to quantum physics. So when it comes to experimentation, I'm particularly interested into quantum optics, which is the study of quantum property of light. And to give you an idea, so here is a quantum computer based on quantum optics. So as you can see, it's a highly complex system with a lot of different optical components, and that require a lot of technical expertise. But in an educational setting, quantum optics is more presented like this. So here you can see an educational kit from Tor Labs, a manufacturer of optical components, that allow to conduct a set of defined quantum optics experiments at an introduction level only. And so if we take a broader look at experimentation, it's an approach that have many advantages. We have various studies that have shown that being active, physically engaged with the concept and investigate, we can really improve the understanding of a complex phenomena. But at the same time, it has also numerous challenges to overcome. So the equipment is complex. Even for a small board like this, the student only end up to manipulate a small part of the experiment and have little feedback, visual feedback on what they are actually doing. The cost of this kind of equipment can be quite high, especially if you need to equip a whole institution. And finally, time is often a constraint because you depend on access to equipment and lab spaces. If we now take a look at digital tools, they are already regularly used in quantum physics curricula. There are two types, the interactive simulation, which just illustrate a concept and by varying one or two parameters, and the virtual labs that are more flexible because here you just build the experiments first and afterward you explain the concept. And even if they both offer advantages in terms of understanding, they are still limited to 2D interfaces used on the web. And the tool are mainly used once during the courses, and afterward it's over. So we are still far from from a real hands-on experiment, and they do not prepare to really conduct this kind of experiment. So what is missing is a tool that could combine hands-on experimentation and the insights provided by digital tools to help the student understand complex phenomena. This will bring together the two approaches and to address student challenge difficulties, while also enabling them to acquire technical skills that are relevant to quantum technologies. So to achieve this, I will place the real experiment on one side of a continuum and digital tools on the other side. And the space that interesting me is the one just in the middle. Here we can find tangible user interfaces and augmented reality. So a quick aside to tell you that tangible user interfaces, TUI, can be defined as a physical form given to digital information. And in our case, TUI and AR will allow us to combine the physical manipulation of optic components while also using projection to display digital educational content. So as a good starting point, I drawn was the Orbit project, which began at Inria Bordeaux more than 10 years ago in partnership with the University of Bordeaux. So the project initially involved setting up a optic experiment called the Michelson interferometer, but enhanced with teaching aids. This project has been continues to be the result of a collaborative effort between computer scientists, educational researchers, teachers in physics and electronics. And the project have undergone several successive revisions over time to make it more flexible, and it serves as a starting point to the work that I'm going to present right now. So we can start now with wave optics. So here is our first project, Orbit. So a physical device that enables the setup of wave optic experiments, but in a fully reconfigurable space and equipped with a self-adaptive simulation. So here is a table which holds a computer connected to two projectors here and here. So the first projector here will project into the vertical screen, which will serve as a replica of a real screen where we display the result of an experiment, for example, in a real manipulation, real experiment. And the second projector here will project onto the mirror that will project back to the table to display all the teaching support, the simulation, and so on. The computer is also linked to electronic cards located below each jack tables, so it can detect whether a component is connected or not. So Obits is used with a physical replica of optical components. You can have like a small overview of them here. Each component is fitted with an electronic board containing its identifier, so it can be recognized, as well as a screw that allows its orientation to be detected. Some optical elements contain mechanical components that can modify the characteristics of optical elements physically. For example, if you rotate a polarizer like this. So the concept of manipulation is, of course, important for learning about optics experiments. It was so important for Orbits to retain this aspect and to enable the students to perform the same action as they would do on an optical bench. But also, we can modify all the physical property of an element directly on Orbit interface to have more flexibility on the setting up the experiment. In terms of simulation, here is how the application works. So we run on Unity and 3D engine that will manage all the 3D environment from array, collision, and so on. But on top of this layer, we have like the whole application, and the optical simulation was integrated based on the model provided by the physicist we work with, who produced the whole simulation. So instead of calculating experimental setup in advance, the Orbit simulation will start from a light source and then calculate a series of light paths that will incorporate the various components of the optical model. Each object encountered along the path will generate a new propagation, which will be calculated based on the characteristic of the object encountered on the previous propagation. So by linking one element to the next, we will reconstruct a chain of propagation until we reach the final display. And we do all of this in real time. Okay, now that I have explained a bit how the tool works, here are two scenarios in which Orbit can be used, and I will go in detail from about one of them. So let's take example of a practical session. As you can see, Orbit provides access to a whole range of information that helps the student carry out the experiment. First, we have manipulation guides here. They will help the students, for example, by letting them know precisely the value they are manipulating in real time. And you have more conceptual guides that will help conceptual learning and link what they are doing to the theory that they saw in the classes. So taken together, all these aids allow us to set up the experiment much more quickly while practicing the same step as a real-life experiment, and also link the theory covered in class to the context of the experiment. So each of these teaching scenarios have been used at the University of Bordeaux of physical measurement since 2020. Are still used to this day. But okay, before moving on, I would like to revisit the framework that I outlined earlier. So the problem is that Orbit alone does not fully replicate all the constraints of a real experiment. In particular, how can we continue to conduct hands-on activities when physical facilities are inaccessible or in crisis situation? We do not cover this part with Orbit. So the idea was to combine Orbit with the more traditional virtual labs so that I could expand the range of teaching scenarios in which the tools can be used. So starting with Orbit, a second app has been launched with the main design philosophy being that the user can switch between Orbit and so Shire, simulation of Orbit for interactive and remote experience. It's a fully digital alternative to Orbit that offers the same element, the same teaching guidance, but on a computer. And so while working on my thesis, I used my research to try to reinforce the link between the digital and the real experiment, which is the main difference. First, through interaction, because obviously the main drawback of purely digital tools is that you cannot physically manipulate all the elements. And so by collaborating with physicists and electronic engineer, we have developed a prototype accessory that allows users to physically adjust the parameter through an accessory that we plug in a USB port. And so we restore the hands-on experience and enhance the transferability between Orbit and Shire. And also through immersion, we have several 3D models for each element, ones that are closer to Orbit, so that the student can easily navigate between the two, and ones that are more realistic that correspond to actual optical elements. So now to get back to the scenario I presented earlier, we can add one Shire as a demonstration tool, but also a new type of scenario, which is working from home. Now the idea is to build a continuum between all these types of usage. So to answer a continuity of learning outside the classroom, we must achieve multiple goals. First, the continuity of the experience with the ability to pick up where you left off at the lab. Continuity in communication, thanks to a note-taking system that allows asynchronous communication in Shire. And also the ability to learn independently through custom learning scenarios. These three features enable students and teachers to effectively link their activity both inside and outside the classroom, whether they are preparing a class, reviewing their work, or interacting one with the other. Also, the last scenario I'll present is an exploratory approach about remote work with Orbit and multiple sessions of Orbit and Shire. So I was able to carry this work thanks to Nathan Salin, which was an intern at the time, who was primarily responsible for developing the networking between Shire and Orbit. And together we considered all the issues that would arise in terms of interaction and display. And we were able to draw two usage scenarios. The first one involved a single table shared for all users, and the second one involved a table for each user. So this reflection led also to the development of portals, magic tools that enable to transmit discontinuously light without any alteration, and that so you can teleport light from one table to the other, for example. And here we stray off a bit of reality, but we also wanted to explore new tools, new type of tools that would help the experimentation process. So next, I wanted to involve user into the process of creating my project. So to that end, I conducted interviews with people involved in higher education in physics, primarily instructor. And so they could try out Shire freely, and then I did a thematic analysis of the interviews that I did with them afterward. And I will present some result of it. So first, Shire proved to be a flexible and user-friendly tool that offers a comprehensive experience. And three of the participants also noted the importance of clearly explaining the various simulation model, which was not really the case in the version of Shire that tried out. But in response to that, I added first a manual that explained not only how Orbit and Shire work, but also provide an explanation about all the optical simulation and how everything is done behind the scene. And more recently, I've also added automatic warnings that when people reach the limits of the simulation, they can know it and know that the result might not be the same as the one they expect. So it was done especially to make it easier for both teacher and students to use the software independently. So for theoretical learning, Shire was also highlighted for its ability to bridge the gap between theoretical learning and hands-on experimentation. And participants also highlighted the time savings that using Shire would provide during a practical session. Okay, so now that we saw Orbit and Shire, let's go back to the continuum. So I have two tools capable of conducting wave optic experiments. But now these two tools can be used together to create a single system capable of covering a wider range of scenarios, both inside and outside the classroom. So it's with this hybrid system that we will be able to conduct quantum optic experiments. And from now on, I will not distinguish anymore the physical and digital components. So let's talk about quantum optics with the last project, HQBit. So first, light can be broken down in elementary particles called photons. So to unveil quantum phenomena, we must work with single photons to make sure that we are in quantum conditions. So representing this single photon will be at the center of the design of HQBit, so the new project simulation. So the first step is to simulate light sources capable of emitting one photon at a time. So I won't spend much time on this, but just to highlight that the light sources can have different type of emissions. And what we want to get is an ideal photon sources here, where each emission is equally spaced in time, and to be sure we isolate each photons. So in the literature, there are multiple ways to get this type of source. First, we have the macroscopic sources that will approximate the behavior of a single photon sources. So they are the cheapest way of doing this, but also they are not efficient at all. And if you remember the Torlax kits that I presented earlier, they actually use this kind of sources to cut down a bit the price, but it's like really not that efficient. So on HQBit, both of the examples are doable. So we can replicate the experimental process that the student might come across on real life setup. But also there are sources called microscopic source that are actual source of single photons, but are way harder to replicate because they can depend on a lot of environmental conditions, like temperature, for example. And it exists a lot of different types that I won't detail here, because in HQBits, we choose to implement a perfect microscopic light sources. So this allows for the two approach. We have either the experimental approach with the macroscopic sources or the more theoretical approach with the microscopic, the perfect single photon sources. And we can compare it both together. So now that we are emitting photons, we need the tools to detect them. So to do this, I choose to model a single photon avalanche diode, which is a detector commonly used for a single photon detection. And the important thing to note is that they cannot detect photon continuously. They have to cool down between each detection. So a real SPAD is capable of obtaining temporal data on the detected photon. In HQBit, this data is represented by what we call time bins. The boxes here you can see on each line. Each line represents one detector. A time bin corresponds to the time in which the detector is capable of detecting a photon during the data acquisition. So a light-colored box like this corresponds to a time bin containing one or more photon, and a darker box means that there are no photons on this time frame. This data corresponds to the experimental data, meaning that the result you obtain depend also on how you configure your detector. Now, like with wave optics, the goal of the project is to bridge the gap between theory and experiment. So I implemented a second level of information that corresponds to the theoretical data, which is the actual arrival time of the photons on the detector. You can see the little red bar here. This way, we can switch between the two levels of information and use one to explain the other. Also, it's important to note that real SPAD are far from being perfect, and they suffer from defects such as dark counts, additional counts without any photons, that introduce a lot of noises in the data. But in HQBit, we have kept perfect detector as the baseline to explore the concept, but we also leave the option to degrade the detector to actually more closely mimic the experimental conditions. Additionally, I also added a different visual way to represent what's happening on the detector. First, you can see here an electric event that correspond to detector activation. Then you have a visual representation when the precise photon detection is activated. And finally, we can also visualize dark counts, so the noise that I was talking about, which is visual differently than the other one. But HQBit SPAD is not limited to just temporal detection. They also allow for other two types of visualization. And I will just briefly go over the statistical distribution. So it can provide either the distribution of photons across time bins or the total distribution of photons per detections. And on the second graph here, you can see a red line, which is actually the theoretical distribution expected from the type of sources. So during the experiment, students can see the bar chart reconstruct progressively and see if it matches the expected distribution. So there are also an alternative way to link the experimental results to the theory. Okay, now we can talk about a bit more general tools. So as a reminder, here you have an optical setup designed for quantum optics, and here you have orbits. So as you can see, they are not on the same level of complexity at all. So explore different methods to conduct much more complex experiments. So the first method is called encapsulation. So instead of expanding the space of the for the experimentation, I did the opposite. I reduced it to a single erasable element. So this process is similar to some optic setups that contain pre-assembled components, but unlike those, here you can fully explore and modify the interior of these boxes. A second tool is called boards. There are components that can be attached to optical elements to control their behavior. And so they can perform various functions, such as automatic parameter adjustment. And it's important because in many quantum optics experiments, we'll find ourselves switching between two values of a parameter. And at some point, physical manipulation is not really the skill that you need to acquire. It's only burden like the whole experiment. And even they use like a mechanized automatic components to do this in reality. So it's kind of the digital counterpart of this. Okay, so I've taught several teaching scenarios using HQBits, and I will present one of them here. So this scenario is set between classical and quantum optics, where we will observe the difference in emission of multiple light sources. So after setting up the experiment, we'll be able to start simply by observing the difference between the experimental data obtained by the two detectors here. And next, we'll be able to use another element called the correlator, which will allow us to correlate the detector data to calculate the profile that we see here. And here we dive really more into the theoretical side and the mathematical side of quantum optics. And once again, we go from practice to theory. So to end on this, I've also conducted interviews on HQBit, but this time with 9 students. And same as before, I did a thematic analysis of that, and I will present a few results here. So first, about teaching quantum optics, the shut up and calculate culture is still very much alive. I had noted that. And this still pose a problem for some students, but at the same time, it also benefits others. And that's exactly what I was talking about when I talk about multiple student profile. So we need to have tools to talk to both of them. With their experience with HQBit, they appreciated the HQBit ability to bridge the theory and practice, and also giving them access to content that they will otherwise be unable to see during their courses. Okay, so now to conclude on that and to talk about future work. With the work, we can go into several directions. The first is, of course, the evaluation of those tools. This is something that I was unable to do during my thesis because it requires long studies with a large number of participants. But HQBit could be evaluated on many fronts: learning, engagement, collaboration, transferability, and that's kind of process that we started now. And in this regard, we could use an approach similar to a study of an earlier version of Orbit, which demonstrated a strong effect on engagement and contribution to international guidance. But with HQBit, we have a new format, which is the digital version share. So it could be interesting to consider how we evaluate an hybrid tool like this. And beyond education, my thesis also opened several directions in HCI. The first one is collaboration. Orbit is currently at the center of an experimental project aimed at studying collaboration within an educational task. Also with interaction, to dive more into the prototype that we did to explore physical manipulation and create an experience that feels more like manipulating the real thing. And also in visualization, to explore the transition from a concrete data, so the one on the detector, to an abstract data, the one on the graph. And finally, one last area will be to move forward to quantum technology, and particularly to quantum computing. So we have seen previously that quantum computer can be based on quantum optics, and therefore there is a bridge to build between the two disciplines. So this could be achieved by establishing a link between HQBits and tools such as IBM Composer, which allow users to generate a quantum computing tool circuits on a PC computer. And this way we could move from the theory to setting up a practical experiment and then transitioning to a concrete application. So we have like a whole even more teaching scenarios to encounter. Okay, to conclude this presentation, I'd like to discuss the Schrödinger cat experiments, which has become quite popular in the general public. So a cat that could be in superposed states, both dead and alive at the same time. And in reality, this tough experiment was conceived by Erwin Schrödinger to demonstrate that certain aspects of quantum physics are completely absurd at our level. But that doesn't mean that we can limit to understanding only phenomena that happen at our scale. Learning concepts that challenge our everyday perception of the world is difficult because it requires us to question what we perceived. And that's why I believe that creating tools that help make this concept less opaque is important. And especially since quantum physics, like AI in the past years, may take more importance on our everyday life in the future. And so if the tools that I make can better prepare the newer generation to this kind of thing, I will be really happy with the outcome. Thanks for your attention, and I will take your questions now. Thank you.